Okay, as we continue to pursue sustainable energy solutions, hydrogen energy is emerging as a promising option with the potential to transform the energy landscape. However, like all energy developments, it is important to understand and manage its environmental impacts, particularly its effects on water resources. It's my pleasure to introduce Dr. Ning Lin with the Bureau of Economic Geology. Dr. Lin is a chief economist at the Center for Energy Economics and will share her expertise on hydrogen energy and its impacts on water resources. Please join me in welcoming Dr. Lin to the stage.
Can you guys hear me okay? Okay, good. Well, I have to say it's my first time to come to the groundwater summit. Thanks for the invitation. So I come from the energy sector as an economist, so I'm here to learn a lot. So even just this afternoon, I learned so many things that I have not really get exposed. So basically, I came here to share a little bit of point of view about hydrogen. Since you guys probably, water and energy often crisscross in terms of a lot of subjects, so you guys probably get exposed about, in the energy sector, we have this big, movements towards hydrogen or hydrogen value chain. And I just want to share some of, the latest status of how that is going for US as well as for Texas. And very specifically, relates to this group. What is the type of water impact, at least, from my group and the Bureau of Economics Geology, what do we think? Okay, so just a little bit, for those not familiar with the Bureau of Economics Geology, we're a research institute, part of the UT Austin, and we're also the geological state of Geological Survey of Texas. We provide research for energy, environment, and economics. So the type of work that we're doing right now on the hydrogen is part of an industry consortium called GeoH2. We work on various topics from geology, engineering, and also economics for hydrogen. And we started this journey about 3 years ago. Okay, so that's the team. So today, for my topic here, I'd like to just cover a couple of things. First, for those that probably not as familiar, I will talk a little bit about hydrogen's role in the low-carbon economy, why we care about hydrogen. The second thing is we can talk a little bit about the development recently in the US and Texas, and what it does mean for the state of Texas. Also, we can dive a little bit into the hydrogen production pathway, talk about where and how much water they use for each of the pathway. In the end, I will wrap this up talking about, at least from our view, what is the aggregate picture of water usage for Texas from hydrogen. So why hydrogen? Well, I think the very brief answer for this is hydrogen is introduced and expanded in the system recently by policymakers try to further reduce the emission. It's really because of trying to find more additional low-carbon solutions. Why is hydrogen? Hydrogen is very unique. First of all, if you can see this value chain, it kind of covers from the production side, from different feedstock for producing hydrogen to the transmission as well as storage to the end use. The part about hydrogen is very unique is, first of all, hydrogen can be produced by multiple different production methods. It can come from natural gas, it can come from coal, nuclear, renewable. So pretty much a lot of different existing energy sources, it could actually lead to production of hydrogen. So which gives hydrogen a very unique advantage to enter the energy system and complement other technology. So that is kind of then the versatility and adaptation of hydrogen into the energy system. And once it's produced, hydrogen can be transported by pipeline, liquefied, or actually transformed or converted into other fuel or ammonia or e-fuel, e-methanol and synthetic fuel, and for the various downstream applications. One of the most important application for hydrogen, like I said, is really about reducing, emission. It's for a lot of those chemical refineries, as well as cement and steel. There are a lot of industry. It is very difficult to electrify because of the process design. So hydrogen enter those segments to help to abate their emissions. That's what we call hard abate sectors. So that will be at the front for the hydrogen use. And the second and third would be long haul, heavy transportation, as well as power generation. Power generation right now, what we're looking at is using hydrogen as a more stable long-term energy storage to back up intermittency for renewable electricity. So as this is a value chain. For the US right now, US actually produce about 10 or 11 million metric tons of hydrogen. That is about 1/7 of the whole world. So the whole world has 70 million metric tons. Most of the hydrogen produced today is from natural gas, from steam methane reforming, which is a blue color of the pie chart. We have some yellow, which is from coal gasification worldwide. Mainly that is in China for the coal gasification, but generally comes from fossil fuel of hydrogen. And for very, very little part from electrolysis. For the right-hand side, we have the map of US. US is very unique in the sense that we have, first of all, you can see the dots on the map. These are the existing hydrogen production in the US right now. We can see the cluster in the Gulf states, as well as we see the blue and purple natural gas infrastructure. What we're indicating is we do have a very connected pipeline networks that could potentially be leveraged for hydrogen. And also US have about 1,500, I think it's about less than 1,000 miles of hydrogen pipeline right now for chemical. So as that is the state of the US right now, since 2021, the hydrogen, the Department of Energy has launched the Hydrogen Earthshot. The Earthshot is setting the target to reduce the cost of clean hydrogen to $1 per kg by 2030. So it's $1 for 1 kilogram in 1 decade. And that is about 80% of cost reduction from the today's hydrogen produced from renewable energy, what we call green hydrogen. So that is a substantial reduction and a very ambitious goal by the US DOE. And what it does is actually bring hydrogen from 1% of the energy system in the US to 5%. I always try to reiterate that point because people say, oh gosh, this is such a hype. Well, it is important, but also remember, right now hydrogen is 1%. And the DOE is asking to bring from 1% to 5%. So it's not taking over the world, it's not taking over the whole energy system or the natural gas. It is just from 1% to 5%, which it takes a lot of investments. And one of the things, I'm just going to go through this really quickly, but I wanted to mention to you guys, so maybe you have heard about this. As part of the IRA, the Inflation Reduction Act, there is actually a very important production tax credit. It's called 45V, which is applied for the low carbon intensity hydrogen. It's part of the program. And US has one of the most aggressive measures, I believe, for the production sector for hydrogen. Basically, what is quite interesting is this production credit will give production, hydrogen production facilities tax returns or tax credits for the first 10 years, up to $3 per kg, which is substantial. And basically, it can bring some of the renewable-based hydrogen production costs down to a competitive range with traditional, conventional hydrogen. So that's, and one thing is quite interesting for how US is doing it versus others, like Europe, is US is really not picking the winners and losers to say we want to go with fossil, we're going with nuclear or renewable. We're saying we're counting for the life cycle of the carbon intensity. So if someone could actually have a plant with lower carbon intensity, even you come from fossil fuel or nuclear, by the regulation, it is not ruled out. So it's not picking the colors or the production pathway, but it's very much focused on the carbon intensity. And one of the latest movement for the U.S. is last September, the U.S. Government has announced 7 hydrogen hubs. Backed by $7 billion. Later on, they threw in another extra $1 billion. So total together is $8 billion for 7 hydrogen hubs. And for Texas, we're proudly present, and we actually have one of the high velocity. Maybe some of you guys are working with those guys, but that's the Greater Houston area's high velocity hub. That is one of the hub being selected, and UT Austin is actually part of the team working on the application. So these hubs are really a cluster of projects from production, storage, and transportation and downstream demonstration for hydrogen, and is a way to try to quickly accelerate the development by the US DOE. So I think that I wanted to kind of give you guys this chart, which I find it very interesting, because I mentioned to you guys, okay, hydrogen is important, so how important is? So the National Petroleum Council came out with a report actually earlier this year with a very extensive study that, our team is also part of the team working on this report. What came out is something very neat. It talks about 2 different states of the U.S. reaching net zero. So the blue line is the state policy. Basically, if we're just going as the U.S. current policy, as we can see, that the U.S. will not be able to reach emission net zero. But with the red line, which is a much more aggressive intervention in a lot of areas. But for this study, it tries to identify what is the role of hydrogen. The hydrogen would be able to close about 8% of that gap of the net zero 2050 goal for the U.S. by deploy hydrogen at a more aggressive scale, and that will save about 0.5 to 1% of the GDP. So basically, it's trying to quantify what is the role of hydrogen in helping U.S. Reaching the net zero scenario. And in that scenario, this is basically a projection of hydrogen. Remember what I was saying, that first, right now we have about 10 or 11 million metric tons. So in the state policy scenario, the whole US probably go up about triple the size, right? So about triple, 30 or 40 million metric tons. For the 2050 case, we can go all the way up to close to, I think, 60 or 70 times, so 7-fold of the growth of hydrogen. And that is really come from industry. That's what I was saying, the hard-to-abate sectors. That would be your refineries, your chemicals, cement, and steel. And then there's other ones for, transportation, export, some of them, as well as power generation. How about for Texas? So I kind of talked about US. For Texas, the left side of the map is actually the emission by EPA's flight database, basically looking at a lot of different intensive emission from those hard-to-abate sector. So in order to kind of identify where is the markets for hydrogen, we look at where is the most of hard-to-abate sectors in Texas, and which is no surprise. 50% of that is gathered around Texas, the Greater Houston area, and 50% is around other parts of the state. That's why the high-velocity hydrogen hub is located in Greater Houston area. On the right-hand side is a map of our, oil and gas drilling activity, as well as our renewable resources. Basically, the idea is, right now we're building a hydrogen hub in the Texas coast, but there's a lot of work and interest around the state to understand where will that be infrastructure built. It could be beyond, the immediate Houston area. And for Texas, this is also one of the results from the NPC study. It talks about, we talk about what's the total demand for hydrogen in the US, but for Texas, as you guys can see, that Texas is really leading the hydrogen market development in either scenario, by far the largest pie. And one of the works that I want to mention here is for the Bureau. We have been working with different industry partners as well as different projects since 3 years ago. Besides of focusing on the obvious Greater Houston area, there is a lot of interest about Permian Basin, naturally because Permian Basin has cheap natural gas, we have renewables, and we have basically stranded natural gas right now. So the idea of introducing additional clean hydrogen energy projects in the Permian as well as the West Texas area, it has been a focus for the Bureau's work. This is actually a chart. I don't want to go through every part of this, but I wanted to mention to you that the main part about hydrogen production is really two parts. One of them we talk about from natural gas. That's the top two. They're what we call steam methane reforming plus CCS. So now we, besides of the traditional way, we actually capture the carbon dioxide, or the ATR, which is autothermal reforming, which is slightly more, I will say, advanced process, also from natural gas, reforming of producing hydrogen. And both of those, they use water, right, as actually key components of the reforming process of generating steam, as well as doing post-processing. And not mentioning that when you have the CCS components, you also have water requirements for the CCS as well. For the other part, so this, for the natural gas with CCS, generally we call blue hydrogen. That's kind of a term you probably heard people say, blue hydrogen. Blue hydrogen means from natural gas with CCS. The green hydrogen comes from renewable electricity and going through splitting water. So obviously there, water is also a very key component of the reaction. And as in order to do that type of reaction, you will need about 50 or 75% of your total water actually will be wasted because you have to go to the high purity water for the whole process. And also the water usage will be the processing of the, after the electrolysis process. And that is producing hydrogen, and generally that hydrogen can be stored in a fuel cell or in other forms to go to the end use. I actually, just to talk through this is actually a table that we gathered together of all the information of what is, natural gas-based production routes versus electrolysis production routes of water usage. Generally, kind of a couple of key takeaway about this. You will see a lot of number in the literature. We spend a lot of time trying to comb through. There's a couple of things. Water can be used for process. It could be used for cooling and CCS. Depends on what type of literature that you're reading. The number could be all over the place because of the nuances of those definition is not clarified. So be careful if you're looking at some literature that if it's not apple to apple. Frankly, we're still struggling with that. But I wanted to share with you guys what is our latest point of view. And for the water cost part, I'm just going to go through really quickly, is for example, for a Texas-based, blue hydrogen process, we see it's about, $1.57 per kg of hydrogen. Among that, it's about 4 cents for water. So water is actually a relatively small part, and we could do a lot of different variation of the water costs for the levelized cost of hydrogen. But the key takeaway is you're talking about 4% of your whole levelized cost for water on the blue hydrogen route. For the green hydrogen for electrolysis, for Permian Basin, it's actually $5.70 per kg for levelized cost of hydrogen. In there, that water cost is about 3 cents. If we're actually using about a half cent per gallon of rate of the unit cost. But even you can see that it's still a very small part for the whole cost. What we're trying to say is water is really important, and managing water is important, but there is a lot of room for this hydrogen production process to consider different range of water. They could use fresh water, they could use treated water. We have done different projects. They are very interested using, desal with, for their water and different things. But running the economics tells us on both sides of a hydrogen production scenario, water is important, but because the cost is relatively low in the whole entire levelized cost, there is a lot of room to play for the hydrogen project to optimize or consider different options for water. This is kind of my last slide. As we talked about on the facility level, how water is important, but in terms of cost, relatively small for levelized cost for hydrogen. How about for the state level? So if our Texas state really spun off doing a whole bunch of hydrogen projects, what does that mean for our whole state in terms of water usage? Well, if we take earlier the case I was showing you guys of an MPC study of net zero 2050, so that is kind of the biggest dream that we have, biggest number we have for Texas. If we take that number, that is about 44 million metric tons by 2050, so fourfold from what we have for the production of hydrogen. And if we take that number, we do the analysis looking at how much is from green, the renewable electricity, or from blue, for natural gas, routes of hydrogen, how much water in total we need. We run a couple of scenarios. One of them is 80% coming from natural gas, 20% from renewable electricity. The other one is a flip, 80% from renewable, 20% from natural gas. And the last one, I just say, let's do a most conservative case. But all in all, in that chart, what we show is, with all the scenarios, in the end, the highest, by 2050, the water usage for hydrogen production is about 1.2 to 1.8 trillion liters. Sorry, I did not use probably gallons, but you guys can do that in your head. But the whole point is by 2050 is about the highest we can see, is the most conservative numbers, 1.8 trillion liters. I checked a little bit on the research. That is a fraction compared to oil and gas water usage as agriculture usage for Texas. I guess the key takeaway from this work, what we see is there are a lot of people ask us the very first thing is about water when they talk about a hydrogen project in the recent years. They're very, very worried. But based on everything we have seen and talking to different industry partners and projects, water usage for whole hydrogen sector shouldn't be a very significant component or threat to the state of Texas as a water balance. Yep. And I think that's, thank you, end of my presentation.